look what I got in the post. Yes, for those of you who have realised I like all things DEC, I am finally going to have a DEC mainframe in my living room. Now, as you might have guessed, not a full-size one. I mean, no one has a living room that big, right? But this scaled-down replica of the front panel, known as the PDP-10, which I'm going to have a great time building, and I'm also totally going to use it as an excuse to look at the history of DEC mainframes and the PDP-10 in particular, and all the exciting things that happened with it at the MIT lab, a lot of which shaped the modern world in which we're currently living. So, buckle up, it's about to get nerdy. But before we get to the really nerdy stuff, I need to tell you that this video is sponsored by PCBWay. Fine purveyor of printed circuit boards. Yes, for all those who've been looking for a good way to join their components together, you might find a thing known as a printed circuit board is a really handy way of doing that, and PCBWay makes printed circuit boards, hence the name. I bet you thought there was just some form of YouTube sponsorship program, but no, they actually do something useful in this world. So if you're the sort of person who likes joining electronic components together, you might want to consider a PCB from PCBWay. The world of mainframes holds a little bit of mystique, as a mainframe's not the sort of thing you get to, well, play with. They were, and still are, horrendously expensive, and even the biggest of corporations might have one or two. However, thanks to Oscar and his kit, well, I'm finally going to get to actually play with one. While I'm just about old enough for mainframes to still be in significant use, I'm not old enough really for them to have been not considered more of a legacy device, and for most businesses I've been involved with to, have one. Except for when I worked for ICL for a little while. I mean, they made mainframes, and therefore had a surprisingly large number of them still just kicking about and doing things. Mostly doing stuff for their customers, who are now paying ICL to essentially babysit their mainframe so they didn't have to look after it themselves. But the last thing I was allowed to do with these things was play with them. So they have this mystique as this large, powerful, big iron that you never got to touch or see, and yet made the world of big corporate data move. They're the core of the banking system, the airline system, the tax system. You definitely don't have one in your living room. Well, till now. Now what I have here is a scaled replica of a DEC PDP-10, DEC's entry into the mainframe market. It is based on an earlier DEC machine, the PDP-6, but when it comes to PDP-6, DEC seem to avoid using the term mainframe, as to most of the world, a mainframe was a thing made by IBM. But by the time we get to the PDP-10, DEC is the second largest computer company in the world, and it wants the world to know it's making a mainframe. It is going to compete with IBM. Now that's a pretty bold decision for DEC to have made, as other companies have tried competing with IBM in the mainframe space, and, well, they've not done overly well. In the US, the mainframe market really kicks off in the 1950s, and the main player in it is IBM, and you also have the other players which are referred to as the Seven Dwarfs. Although two of the most well-known names in that market, RCA and General Electric, I mean, they're well known for other things, they dropped down to the market relatively soon, and the remainder were known as The Bunch, because they're Burroughs, Univac, NCR, Control Data, Honeywell, hence Bunch. Outside of the US, you typically have a national champion in that domestic market, often essentially blessed by government. So in the UK we had ICL, in Italy they had Olivetti, Germany had Siemens, Japan also had a surprisingly large number of them in the form of NEC, Oki, Hitachi, Fujitsu. Fujitsu very much still being in that market today and helping to jail postmasters across the world, or at least in the UK. So deciding to be a new entrance into that market is a bold move. And it's not a big market in terms of the number of units you will ship. It's a big market in terms of revenue though, because there are not a lot of major corporations that are big enough to go around buying a mainframe. And a lot of corporations that are that size have already bought themselves a mainframe and are possibly even on their second generation of mainframe before 1966 when DEC's PDP-10 comes out. And the problem if you're one of DEC's sales force going to one of these major corporations and trying to sell them your new shiny mainframe is that your new shiny mainframe will not run the software that's on their old not so shiny mainframe anymore. Also, IBM has a pretty compelling lineup with their System 360 series of machines because you can buy yourself a little mainframe, well, by little I mean could fill a house, and you can buy increasingly larger and more powerful mainframes and run the same software that you ran on your little mainframe. Again, definitions of little are relative. So those looking to upgrade their mainframe have a pretty compelling reason to stick with IBM. But DEC's not building on top of nothing. They have a PDP-6 customer base that they can build on top of with the PDP-10, and DEC Box is pretty clever on this one. They find one of the few market segments where there are organisations who either currently don't have a mainframe or do not mind trying something new, and have the sort of resources you can use to buy a mainframe. Yes, the PDP-10 has a lot of success in the university, educational institute, and research corporation space. Trying something new is kind of the reason they're trying to buy a mainframe in the first place, so they are not beholden to IBM in any way, and DEC's mainframe does come without a lot of IBM's baggage from the late 40s, early 50s. And this is probably one of the markets where the PDP-10 is its most successful. And if we look at an early map of the internet when it was still ARPANET, we can see that by and large that system existed as a way to connect PDP-10s together and the occasional PDP-11, and the odd thing made by IBM, the map sort of gives away the dominance of the PDP-10 in the market space that, well, ARPANET was being built in. So this is why the PDP-10 has an outsized impact on our stories of the past from the internet, and also what would come after it. Because if you were involved in the early internet, ARPANET, you were probably using a PDP-10. Now, before we get into having a look at the kit and the sort of things that we can run on it, I should probably have a little look at the original hardware for the PDP-10. Now, the first thing I should probably point out is the PDP-10 is not just one computer that they kept making from the 1960s all the way up to the 1980s. There are lots of different variations or models of the PDP-10, including different central processing units. And by that I don't mean a little silicon chip, I mean an actual big physical unit. The underlying technology for these processors also changes dramatically over time. In the 60s we start with little discrete transistors, all put on a card, known as a flip chip, and then these flip chips were all linked together on a backplane which was wire wrapped in a semi-automated way. In later models we start to see microchips getting used, but again this is not a processor on a chip, this is a whole bunch of TTL logic chips all linked together. Later on we also see the shift to emitter-coupled logic, with each of these major changes in technology being introduced in a new version of the processor. But even within the major processor versions, we also have sub-versions within that. So for example, you could have a different caching and page controller. So they could be a bit mix and match. We also start out with core memory, which is a series of ferromagnetic rings where each ring represents one bit. So later on we start seeing DRAM technology start to appear. Some of these CPUs are actually got multiple processors in them, but all the systems also have what's known as front-end processors, which is essentially in a lot of cases a PDP-11 that's doing the system's I/O tasks. And again, the underlying technology in those FEPs changes a lot over time as well. So these are big complex systems with a myriad of things that can essentially make the system up, which means that DEC can essentially customize the mainframe that you get for your needs. Because tailoring these systems, well, at the sort of prices you're paying and the kind of volume that's being done on these things is perfectly feasible. Now let's get a look at the kit itself. Now, as the name PyDP probably gives away, this thing does have a Raspberry Pi at the core of it. That's where our PDP-10 emulator's going to run. It'll also emulate a number of peripherals for the PDP-10 as well, including an entire PDP-11. We will come back to this. Now, the main part of this kit is essentially the operator panel for the PDP-10, which means it comes with a lot of LEDs and an incredible quantity of switches. Now, I love the care and attention Oscar's put into this thing, with all the mouldings, getting all the plastics right, all the switches right. The time and effort he must have put into this is absolutely incredible. So I think at this point we should probably get on and build it. Cue the soldering montage music!
I'm another SOS, written with invisible ink. Someone's been shooting bottles just to see how fast they'll sink. If you found me, would you know me? The ocean washes things clean. When you want me, I'm a warship. When you hurt me, I'm a dinghy. When you need me, I'll always be.
This little bit's where it reminds you of which side to solder the connector for the Raspberry Pi. I'm not sure Oscar put here entirely for me, but when I built his PDP-11 kit, I did solder that on the wrong side of the board last time. So I hope I'm not the sole reason that wording's there.
I've walked so many planks that I'm running out of deck. If you'll be my foghorn, then I'll be your shipwreck. So darling, don't fall a dinghy. When you need me, I'll always be a submarine.
Now we've got all the PCBs soldered together, we just need to link the PCBs with this little cable and get them all assembled into their case. More montage music. So we now have our finished PDP-10, and to be honest, it looks amazing. I am very pleased with how this looks. But as it's built, we can now get on and get some software on this and start playing with our PDP-10. Now, I'm going to very quickly rush over the install here, because, like me, I'm sure you all want to really see what this can do rather than me installing it. So we just have a regular Linux install on the SD card, and onto that we put all the emulator software and all the disk images, which is all in this handy repo. Now I should mention, this bit contains the handiwork of an awful lot of people. This is not just Oscar. Oscar designed and did all the PCB stuff and all the nice injection molding plastic, but the emulator itself does predate this, and others have helped him tailor this to work with his kit. But I think the most impressive thing here is the way Lars has managed to gather together stuff from a whole bunch of people to help make ITS a thing that we can boot and run again, and have a number of applications running on it. Because there's some pretty exciting stuff in here. because this machine represents the beginning of online multiplayer gaming, CP/M and thus DOS, the beginnings of Microsoft itself, and the open source movement. This machine has an incredible significance in terms of the founding of a lot of the stuff we've got now, and that's not even including all the internet stuff. So I'm going to start with DEC's operating system, before I start talking about MIT's one. Now, the original operating system shipped with it was known as Monitor, and that was later renamed as TOPS-10. Now, TOPS-10 would also form the basis of a number of other operating systems put into use by others. So, for example, Stanford's Waits operating system was based on TOPS-10, and also CompuServe had a time-sharing operating system that was again based on TOPS-10. Yes, the original basis for everything that CompuServe did was TOPS-10 and running on a PDP-10. BBN, the company that was by and large behind a lot of the early internet infrastructure, it developed its own system, again based off TOPS-10, known as 10X, short for 10 Extended. Now, TOPS-10 itself is a multi-user operating system, i.e. multiple people can use it at the same time, each sat at a different terminal. And there was something referred to as a scheduler, which would sit there running on the main CPU, scheduling, running blocks of code belonging to each of the tasks connected to each of the users. And the scheduler had the concept of prioritized run queues, and different processes would be attached onto different prioritized queues based on the priority of the task. In fact, a later release of TOPS-10, version 7, would introduce the idea of symmetric multiprocessing into scheduling, so we could actually have different tasks running on different CPUs, in the same way we do now on modern computers, rather than the master-slave relationship that was in there before. The operating system also provided a shared memory feature, so multiple tasks could share sections of memory. Now, this was put to incredibly good use, and introduced some stuff that was very new then, but would kind of be taken for granted later on. So, shared memory allowed you to create things like multiplayer games. Now, one example of this is DEC Wars, which is a multiplayer version of the Star Trek game. Now, it was developed by the University of Texas, and was based out of a two-player version of the game known as War, which originally they'd written for their CDC 6600, which is an epic use of one of the world's only supercomputers. But with the shared memory features on TOPS-10, they were able to develop a multiplayer version for anyone running on a terminal connected to the PDP-10. Now, any CompuServe users listening to this may think, that sounds familiar, and yes, it should be, because CompuServe did take DEC Wars, remove the copyright notices, and call it Mega Wars. Speaking of things that CompuServe would, let's say, borrow, there was an application known as Forum, which is one of the first CB simulator applications, which is effectively just a chat room, that appearance-wise looks very similar to what you might get out of an IRC client. The other big thing to get written for TOPS-10 is the forerunner of today's MMORPGs, MUD 1. Now, MUD 1 was the first ever MUD, unsurprisingly based on the name, I guess, where MUD stands for Multi-User Dungeon. Now, I'm not going to dig into this too much because, honest to goodness, I want to do a video about MUDs at some point in time and not sneak it halfway into this video. But you can think of a MUD as a text adventure game just with lots of people playing it at once and being able to interact with each other. And in the early internet may have been the most addictive form of gaming known to man. But that all started here on TOPS-10 and a PDP-10. Now, if you were to use TOPS-10, you'd find it weirdly familiar, or at least those who have used DOS or CP/M would find it weirdly familiar, as CP/M is very heavily inspired by TOPS-10, or at least in terms of the command line environment. It's very different in terms of capability, because the underlying hardware it's targeting had very different capabilities. So CP/M is not multi-user, it's not multitasking, but a lot of the commands you'd use to drive it, well, they're basically the same. The whole concept of a file having a three-letter extension at the end to denote what the file type is, that comes from TOPS-10. Using slash to separate directories, that comes from TOPS-10. The way wildcards work for selecting multiple files, again, comes from TOPS. And of course, that's because Gary Kittle, who developed CP/M, was himself a TOPS-10 user at one point. So, the first successful operating system to run on microcomputers is very heavily influenced by TOPS-10. And of course, Microsoft's DOS is itself heavily influenced by CP/M and therefore TOPS-10. Although, there is another connection between TOPS-10 and the DEC System 10 to Microsoft, as that's the platform they originally used to develop their version of BASIC on, which until DOS came around was basically the thing that Microsoft was known for. It provided BASIC to most of those 70s early microcomputers, and in a lot of the 80s home computers. So TOPS-10 is hugely influential on things that became massively more successful later on in the wider microcomputer market, like DOS, and therefore Windows. Heck, even extensions like .exe and .txt, they were the ones used on TOPS 10 for exactly what you think they are. Now, I said I'd also talk about MIT's operating system for this thing. Well, now's the moment. And I must admit, apart from building the kit itself, this is the thing I was most excited about. Because this is something I've read about, heard stories about, but until this point, there was no chance of me ever actually getting to try any of this stuff. So why is this stuff so exciting to me? Well, this is kind of where hacker culture and the whole internet and ARPANET culture really got started. It's also the beginning of the free software movement. Out of the MIT lab came things like the GNU Manifesto and the early open source licenses. It's where Richard Stallman was working. And all of these ideas, concepts, they all took form on their PDP-10 machine, and with their operating system, the Incompatible Timeshare System. Now, I probably should mention that the name of that operating system, the Incompatible Timesharing System, was given to it by the person who wrote the kernel, and whose name's going to come up a lot later on, Tom Knight. And it's kind of an in-joke, because before you had ITS, you had the Compatible Timesharing System. And in fact, the reason they developed ITS was because they didn't like the direction in which the successor project, the Compatible Timesharing System, was taking, known as Multics, which Unix fans are probably fairly well aware of, given it inspired the initial development of Unix. But I have digressed. Back to ITS. Although ITS was developed by MIT's AI lab and was running on their PDP-10, I don't want to leave you with the impression that this was all just MIT. One of the big things they let happen with their machine is they would basically allow anyone to log in, either at MIT or remotely over ARPANET. So there was a lot of cooperation with other labs in different universities, particularly Sale Stanford's AI lab. So this is why this hacker culture grew up around this. You had a key group of people all together in MIT, but also you had people from other parts being able to log into the system and take part as well. Now, before we delve into actually looking at this system in use, because now we've got one, we can play with one, I thought I should talk about some of the features of the operating system, because ITS is where we see some of these features for the very first time in an OS, even though later on, these sort of things would become relatively standard. Firstly, it had a mechanism for letting you set up virtual devices that were running in software, so a user space process could provide the facilities that behave like a device. So, for example, this virtual device mechanism was used to implement file access between machines running ITS, so you could access files on a remote machine just like you were accessing them locally. It had a system for implementing software interrupts, which means suddenly we can have asynchronous user space programs. There's quite a clever tree structure to its process management system, so processes could be run and prioritized as groups, for example. We also get something pretty clever going on with terminals for the first time. Now, this is not the first system to have remote terminals, not by any stretch of the imagination. But prior to ITS, the code to deal with those terminals had to essentially be hard-coded. You had to know which device you were talking to it, and talk to it in the way that that device would understand. In ITS, an application outputted a standard format for doing screen control in ITS, and the operating system would translate that to the calls that need to go to the terminal to make what you've requested happen. So this is the first time we get proper device independence when it comes to display output. You can think of this as Unix termcap system before termcap and Unix were a thing. It also had the same sort of shared memory features that we had on TOPS 10 as well, but they didn't get invented here, obviously. It did, however, miss some things that you might assume an operating system like this might have, and that's a full hierarchical file system. It did have directories, but not as you think of them now. There was the master file directory, which is abbreviated to MFD, and then there could be one or more user directories, UFD. However, none of these directories could have subdirectories. So yes, there's more than one directory in the system, but no, there are no subdirectories, so it's not a full hierarchical file system. And this is also the same layout that the compatible timesharing system had as well. In order to boot ITS, we first have to load its little bootloader. Now, this is done as a paper tape, well, an emulated paper tape, so we have to hit the stop button on the console, followed by the read in button that causes the machine to read in from the paper tape. And once the paper tape's read in, we'll get this line on our teletype that we can then type in ITS, followed by escape and G, and ITS will start to boot off the emulated hard drives. Now, once ITS is booted, I'm going to log into ITS, this time not using the teletype, but using one of the other emulated terminal types. Now, we've got a few here we can choose from. We have a VT52, which is like a dumb terminal. In fact, it's one of the original ones that DEC produced. And we also have the Night TV terminal. This is a bitmap graphics display, in fact one of the earliest bitmap graphics displays, so we have a somewhat more modern display type here, which allows us to do text and also graphics at the same time. Don't worry, we're going to cover this in a bit more detail later on. The other display type we have is an emulated vector display, which is based around an old radar tube, and have been something that PDP machines have had since the very first PDP-1. Now we'll start with doing some basic stuff on an emulated VT52. So we start by pressing Ctrl Z that wakes the terminal up, we can then log in, and then we're into ITS and we can start issuing commands to run software and move around the directory structure. Now you're probably all vaguely familiar with the VT52, or at least things that are very much like it, and on the PDP-10 it was plugged into what's known as an FEP, a front-end processor, and that provided all the RS-232 ports that the terminals would connect up to. The next terminal type we're going to look at is the Night TV terminal. Now these ones are a little bit different. They connect up to an FEP, just like the VT52s, but this FEP is a little bit special. This FEP is in fact its own separate computer, a PDP-11. In fact, some companies or organisations would use this as the only computer they had in their entire organisation, and here we are, using it as a front-end processor for some terminals. So for each of the Night TV terminals, we've got a graphics card essentially in this PDP-11 that takes what's in memory and generates a video signal from it. That video signal was sent over what appears to be a coax cable to the actual screen display of the Night terminal, and then there's what appears to again be a serial port coming back from the keyboard that's part of the Night terminal. So the actual terminal part of the Night TV thing, that's just a basic CRT and a serial keyboard, or at least I'm assuming it's a serial keyboard. It seems to be quite hard to get actual documentation on this thing. All connected back to a card inside the PDP-11. Now that PDP-11 is acting as an FEP to the PDP-10, and the display memory in the PDP-11 is mapped into the memory map of the PDP-10's processor, so the PDP-10 can write to some memory addresses, which are mapped to the physical memory inside the PDP-11. So software running on the 10 can set values in RAM, that gets pushed across to the PDP-11, which that video card then generates the display from. So thus, we can have applications running on our PDP-10, writing into RAM, changing the display that's on the Night TV. Now we've got a nice little demo of this with big clock and little clock, and you can see it can, one program can keep updating the display, while another one is still outputting text to this thing. So although the app that's doing the clock needs to know what to write into memory to get the Night TV to actually display the clock, the other application just uses the standard text handling system, so the application comes out on screen like it would do on the VT52 or on the teletype. The person writing the text application doesn't need to know the difference between the displays, they just write a standard ITS text application. The operating system just takes care of getting that into whatever format that output device needs. Now you will not die of shock to hear once we got the first bitmap displays, the first computer games to make use of it followed very shortly afterwards. Now being a DEC machine, the already very popular Space War was ported to the Night terminal very quickly, as previously this ran on the radar screen, essentially the vector display, but now here we are doing it as bitmap graphics. And this version could run multiplayer, so one person could be running it on one terminal, while player 2 is on a different terminal. Now keep in mind, this is the early 70s. Microcomputers still not a thing, and even when they do become a thing later on in the 70s, we're not going to see this kind of multiplayer on different displays until into the late 80s, early 90s. So not only do we have one of the first ever bitmap displays, we're also doing multiplayer gaming in a sort of way we wouldn't see until decades later. Now, before I get much further on with discussing Night TV, I should mention that Lars, the person who I mentioned earlier, helping to put all this software together so we could see it, is also the person who put together the emulation of Night TV as well, and added that into SimH. So it's thanks to Lars's efforts that we actually get to, see and use this ourselves, something that I'd only heard about of, written up in people's recollections of what times were like in the lab back then. And now, thanks to Lars's emulation, I can actually run software on it and try it out myself, which is not something I thought I would ever be able to do. I'll also quickly show you a picture of the Night TV controller, this PDP-11 I've been mentioning, because you could think from my description that this is just a single PDP-11 machine with some cards in, and it kind of is, but also, as you can see from the photo, this thing is massive. When you added cards to a PDP-11, they didn't go in the box that was the PDP-11. It's not like a PC slotting cards in. No, all the stuff was outside of the PDP-11 mini computer, or at least at this point, and this thing filled racks. It's also been interesting reading up on some of the history of the motivations of why they did this. Now, one of the motivations was that Intel had started to make DRAM chips, and this gave them a way to test these things out in a low-stakes sort of a way, because if a bit flips in a frame buffer, well, yeah, you end up with a stray pixel on screen. Oh no. If a bit flips in your main system and your machine crashes, yeah, no, that's worse. There's many people on this thing. So this gave them a way to put these chips under proper load in a way that people would see errors, but it would also be non-fatal. So apparently that was part of the motivation in creating these frame buffer cards that became part of the Night TV controller. Also, let's face it was also kind of cool as well. So you might be wondering, performance-wise, how does this mainframe compare to, say, a modern computer? Well, I am simulating it at full speed on a Raspberry Pi, including all its FEPs, so that gives you some idea as to the power gap between a modern £50 single board computer and the PDP-10. However, if that's the only impression you got while watching this video, I would be doing a bit of a disservice to the PDP-10, as things are a little bit more complicated than that, as it is a lot more capable than that gap in power would suggest. Now, the main processor is clocked at 500 kHz, which may not sound very quick, because it isn't, but the CPU is operating on more bits than you think it would be at once, because it's a 36-bit processor. Now, to our modern ears, that might sound a little bit odd, because it's not a multiple of bytes. Well, not a whole multiple anyway, but a word length of 36 bits was pretty common in the world of mainframes in the 50s and into the 60s. Things became byte-orientated later on when we started switching to using 8 bits to encode a character rather than 6 bits. But having a bit width of 36 bits means that we can do some high-precision maths operations that for CPUs we'd see coming on later on would not be possible without running multiple calculations. And that meant that when it came to, say, floating point operations, for example, this machine could do about 1 million floating point operations a second, which for the 70s was incredibly impressive. In the 1980s, less so. But performance of the system is not as governed by the speed of the CPU as you think it might be, because we get to hand a lot of work off to our FEPs, our front-end processors. So if, for example, you've got a bunch of graphical terminals, like the Night TV terminals, the main CPU doesn't get involved in running them. The FEP's memory is mapped into the mainframe's memory, and it just writes some values into RAM from the main CPU, and then everything else is done by the FEP. Your central processing unit doesn't get wrapped up in dealing with I/O, for example. Very few I/O devices are connected directly to the CPU. The CPU just talks to things via its mass bus, and then the FEPs get on with dealing with the consequences of that. And that's pretty important for performance when you're running multiple jobs for multiple people on the same system. We can't really clock the CPU up much further than it is, or at least using the sort of technologies it was initially built in, because just the length of the wiring paths inside the thing means we can't drive the clock speed up much higher. Just throwing back to this 36-bit word thing for a second, that's also why we have these 36 switches, labelled 0 to 35, because of course we're 0 indexed, on the operating panel, because that allows us to do a write to a single memory location, because we have to write all 36 bits, as memory is addressable as 36-bit words. The switches on the row above, that's the one that controls the addressing, i.e. which location we are reading a value from on the LEDs or writing to with the switches beneath. Let's have a little look at some of the details of the CPU as well. First, let's start with registers. We have 16 general purpose registers. In fact, that's the same number that an ARM chip has. And each of these, unsurprisingly, are 36 bits wide. Now, in the original implementation of the CPU, the registers were actually the first 16 words of physical memory. There wasn't a separate set of registers in the CPU itself. But then soon we got a hardware card you could add into your CPU to put the registers inside the processor. But they were still also mapped to the first 16 words of RAM, so programs could dump stuff in the first 16 words of RAM and kind of work like a cheap CPU cache. The CPU has two modes of operation, supervisor mode and user mode. Only supervisor mode's allowed to do input-output instructions, and thus talk to input-output devices, and this is the mode that your kernel of your operating system would run in. You then have user mode, which is the mode all your application code works in, and it passes stuff up to the kernel or to the supervisor mode using what they refer to as unimplemented user operations, which was essentially CPU instructions that didn't exist on the CPU that could be trapped in software, and then the kernel could decide to do something with that. that system could also be used to implement in software hardware devices that didn't exist on the cheaper versions of the PDP-10. And by cheaper, I still do mean an ungodly quantity of money. Now, Mac users are probably familiar with the idea of using an unimplemented instruction in the CPU to go from user space to kernel space. Not that there's any memory protection in an early 6800, but that's what the early 68K versions of Mac OS did. Of course, later on that would bite them in the ass as later Motorola CPUs started to include things like an instruction cache and a data cache, and whenever they encountered an unimplemented instruction, they would jump to the handler for that, but they would also flush the data cache and the instruction cache, which meant that every time a Mac application called the operating system, it tanked the performance of the CPU, which is actually the main reason behind why the Amiga could emulate a Mac faster than a Mac could be a Mac on the same CPU. So I think it's interesting to see where early microcomputer, CPUs and operating systems got some of their ideas from. Now, through all these processor upgrades and changes, DEC managed to keep the user space instruction set pretty much the same. So we can take applications from one version of a PDP-10 and just run it on another. Where we do need some changes is to the operating systems themselves that run on top of the machine. As the supervisor mode instructions, the instruction set that let you do I/O and manage the other tasks, well, that does change a bit over time. So operating systems for the PDP-10 do need modifying over time. In terms of networking options, we had two things that were primarily in use. We could have an interface to ARPANET, which connected the PDP-10 directly to an IMP, which is what then passed messages around ARPANET, and there was also a local area network system known as ChaosNet, which I will probably do a whole video on at some point because it's an entirely different LAN technology to everything else you've seen before. But these two different systems meant that you could connect to stuff locally on your LAN or to other computers across the entire of the United States and then later on the world. Well, UCL London to start with. And the ARPANET interface in particular was a key part in helping this hacker community develop across multiple different universities. The PDP-10 also offered a number of other I/O connections which let you directly link terminals to the PDP-10, for example, or line printers, etc. But those interfaces provided a machine-to-device interface, not a machine-to-machine interface. So, what happened to the PDP-10 line? Well, partway along its history, it did kind of split into two platforms, which DEC referred to as the System 10 and the System 20, with a System 10 being a DEC PDP-10 running the TOPS 10 operating system, whereas the System 20 is also a PDP-10, but it's running the TOPS 20 operating system. Yes, if I mentioned earlier that BBN created their own version of TOPS 10, didn't entirely tell you the truth there, because BBN had a hardware paging unit they wanted to get into the PDP-10, which would allow them to do virtual memory, so processors could, use storage as well as RAM. But in order to do that, they decided they were gonna write TOPS 10 from the ground up again to incorporate the changes that they needed for this hardware pager. Hence we get their version of TOPS 10, which is, not strictly speaking, a straight lift of the TOPS 10 source code with changes. It is effectively a complete rewrite, but it has a compatibility layer that lets it run TOPS 10 software. Well, DEC, when they wanted to add a paging system, be it a simpler one, into a later designer processor for the PDP-10, decided to license back off BBN their version of the TOPS operating system, and they called that TOPS 20. And why it has a TOPS 10 compatibility mode and can run most TOPS 10 applications, not all, and you can think of possibly as an intellectual descendant of TOPS 10, it's not actually a source code descendant of it. So these were the two variations with, different processors and memory upgrades, etc. over time that DEC kept offering right up until 1983 when they decided to discontinue their range of mainframes. Just as a brief aside, the System 20 was the subject of the world's first spam email, where the West Coast users of ARPANET sent out an email advertising an event where they were going to let people come and see their DEC System 20, which was sent on the 1st of May, 1978. There's an answer to a very nerdy pub quiz question at some point in your future. So why did DEC decide to discontinue the System 10 and 20 and the PDP-10? Well, their mainframe platform had sold well compared to, say, a lot of other people competing with IBM, but still not on an IBM scale of sales. And mainframes were beginning to seem a bit more old hat and more like a legacy technology, as suddenly microcomputers were now becoming the latest new things, and mini-computers, the thing that DEC essentially helped popularise and turn into something, were more than capable of doing the sort of workloads that had been previously put on mainframes. Not all of them, but an incredibly large amount of them. And the 70s have been a wildly successful decade for DEC, mostly based around the PDP-11, which was their most successful mini-computer offering. Come the 1980s, DEC had created a successor line to the PDP-11, known as VAX. And the VAX range of systems, which DEC referred to as Super Minis, were effectively now in competition with their own PDP-10 range. Now, DEC had started on a project to create the next generation of PDP-10, known as Jupiter. And we do know a fair bit about this proposed system because a lot of DEC's internal documentation is now available publicly on BitSaver. So we kind of know what their development roadmap and plans were. We've got circuit and logic diagram stuff for parts of the machine. So we know the machine was progressing and kind of where it was up to when DEC decided to pull the plug. We also know from interviews with various staff members of DEC once DEC folded that this decision was by and large about the not trying to compete with VAX, and also the cost of developing, marketing and supporting that next generation of PDP-10. So where did this leave MIT and the ITS operating system? Well, to be fair, MIT was already off doing its own hardware thing with its various Lisp machines, even though their PDP-10 and ITS stayed in a significant operational role until 1986, and was kept running until it was finally decommissioned in 1990. Which meant it had an incredibly good run from the 1960s just about into the very beginning of the 1990s. Admittedly, there are a lot of hardware iterations and OS versions along the way, but that's still far more decades than most operating systems get. There was also a computer club in Sweden managed to get ITS up and running on a machine, and they kept theirs going until 1995. And in 2025, I got my own copy up and running here on this little emulator, which thanks to lots of people's diligent work in preserving all of this stuff, you can also do too. The PDP-10 left us a huge legacy. We can trace back things like MMORPGs to the DEC-10, we can trace the beginnings of CP/M and MS-DOS, and effectively the entire Windows line of operating systems. There are applications some of us still use today, like Emacs, started life on ITS running on the PDP-10, and eventually us Vim users will forgive it for that. That general hacker ethos that gave rise to the open source community formed around the PDP-10 and ITS. Some of our early online experiences through the likes of CompuServe, again, all based around the PDP-10, running their own version of TOPS 10. This machine has been hugely influential on everything that came after it. You can point to it and concretely say, that's where this sort of thing started. So in a way, we all sort of owe this machine a debt. And finally, we have a way to actually run it and have a little operator console where we can actually drive the machine as they would have done at the time. Also, have I said it looks cool? Because it looks really cool. If you got all the way to the end, I'd like to say thank you very much for watching. I'll also mention, if you want to know a little bit more about DEC, the company itself, I do have a few other videos. One of them even includes another one of Oscar's kits. Speaking of Oscar, I'd like to say a huge thanks to him for sending me this PDP-10 kit, as if he had not, I don't think I would have had the impetus or a way to get into trying all of this stuff out, and being able to check a number of my assumptions and get this video together for you. Speaking of thanks, I'd also like to say thank you to Richard Masters and Poke for letting me use one of their songs as the soldering montage music. Link below. I also, for once, have some Parish notices, which of course I've left right to the end, so only the most dedicated viewers will hear them. Yes, there's now a Discord server for viewers of this channel, well, and viewers of other channels as well. So Lee, who runs the channel More Fun Making It, which if you've watched this channel you're probably familiar with his stuff, he set up a Discord to talk to people who watch his channel, and then invited other YouTubers to join it, because we were umming and ahhing about making our own Discord, and well, Lee wanted to create more of a generalised Discord, and I thought that might be more fun than just having one, just for this channel. So if you want to come join us, there is an invitation link in the description of this video. And the other notice is, I'm going to Retrofest, which you can think of as the UK's equivalent of VCF. And it's taking place on the 31st of May to the 1st of June, and is being organised by the delightful Pete and Tony from Short Circuit Museum. And it's happening at the Steam Museum in Swindon. If you enjoyed this video, well, YouTube's given you a little button that indicates that fact, and if you didn't, well, technically there is another button, and thanks for the engagement. If you'd really like to help the channel out, you could subscribe, as pressing that button apparently tells YouTube to tell more people about the videos that I make, so some people might actually see them, which would be nice.